So the thing about sequences is I can't give an example. I can't do every possible example. There's strategies that you use, but it's kind of like you'll always come across one that's different than what you've seen before. And so do you have tools to assimilate from other problems to work on and make progress on the current problem? So we talked about these two at the end of class yesterday. So a sequence that's 1 over n to the r. So this is another way to express limit, okay? So by saying the limit as n goes to infinity of 1 over n to the r equals 0, you could also say it this way. 1 over n to the r approaches 0 as n approaches infinity, but that's only if r is greater than 0. So we talked about that at the end of class. So when you're analyzing these sequences, you're on the lookout for this particular form, 1 over n to a power. And if that power is greater than 0, as long as r is greater than 0, that sequence will approach 0 for large values of n. Okay, then we did p to the n. So you think about every next term of the sequence is multiplied by another p. So you have some number, and you keep multiplying by p, what you had before, to get the next term in the sequence. So when will that converge? What if p were 2? We'd have 2 to the 1, 2 squared, 2 cubed, 2 to the 4th. Convergent or divergent? Divergent. That's just going to get really big. So what number that you keep multiplying by itself will result in something convergent? So if your p is between 1 and negative 1, you keep taking a fraction of what you had before. Right? So it's like 1/2 times 1/2. Next one times another 1/2. Next term times another 1/2. Okay? So that will approach 0 as n goes to infinity. So if p is between negative 1 and 1. Now there's a trivial, if p equals 1, it's kind of a trivial case. Then you just have a list of 1s, right? If it's 1 to the n, no matter how many times you multiply 1 together, you get 1. So that would, p to the 1 would be convergent to 1. It's kind of a trivial case though. All right, so these are two common forms to be on the lookout for and to know what's going on there. And then here's just kind of some other strategies. So we talked about considering the associated function, looking at the limit as x goes to infinity of the function associated with the sequence, right? List out a bunch of terms, right? So if you can't make any progress, list out the first 5 or 6 terms and see if you can reason through what's going to happen. You got to know your algebra, your rules of exponents, rules of square roots and other roots. You got to know your algebra to change the forms, so pre-calc knowledge. And then some of this is just common sense. Again, reasoning. Can you use some reasoning sense? Okay, so it's kind of, these sequence problems are kind of like a mixed bag, and so we have some tools, but then we have to have some ingenuity too. You're going to come to sequence problems that you've never seen before. That's just the nature of it. So I want to take 5 or 10 minutes. These were all supposed to appear at once. Come on. There we go. So let's take 5 or 10 minutes to work on these sequences. Are they convergent or divergent? Give evidence, state reasons, give reasoning, and if convergent, determine the limiting value. What does it converge to, the sequence? See how we did. So you should have recognized that first one as p to the n. What's the value of p? So it means every time you go to the next term in the sequence, you multiply the last one by -4, basically, right? -4 to the first, -4 squared, -4 cubed, -4 to the 4th. So it's like as you progress, you keep multiplying by one more -4. Convergent or divergent? Divergent. The only way that's going to converge is if your p is between -1 and 1. That's what we talked about on the previous screen. Divergent because p is not between -1 and 1. Okay, next one. So here I'm showing you that rational, think of that interior argument of sine as a rational function, and we're going to look at the limit as x approaches infinity of this function f. What is the limit of that function as x approaches infinity? So you recognize that because the degree of the denominator and numerator are the same, as x gets really, really big, the numerator is just going to be x squared. And as the denominator, as x gets really big, the denominator is going to end up being like 3x squared. This minus 7 is not going to mean anything when x gets really, really big. So you essentially have x squared over 3x squared, which equals 1/3. So this goes to 1/3 as x approaches infinity, as x gets really large. So we don't want to think about infinity as a number, as a place that we get to, or as something we plug in to other things. Infinity is we're thinking of increasing without limit, increasing without bound. That's the way we want to think about infinity. There's not a destination, right? It just keeps getting larger and larger and larger. That's the way we want to think about infinity, not as a number that you plug into things or that a sequence reaches, okay? So as x increases without bound, the values of n squared over 3n squared minus 7 are going to essentially get equal to 1/3. So is this convergent or divergent? This is going to converge. What's it going to converge to? Sine of 1/3, right? Because the interior is going to get just essentially going to become just 1/3 when n gets really large. So the terms of the sequence are just going to converge to sine of 1/3. Does it make sense? Okay, what about this next one? So this is just an easy version of 1 over n to the r. The value of r here is square root is a power 1/2. From past experience, teaching Calc 2, some of you, or maybe many of you, are going to have to review your rules of exponents and roots, because you got to have this for the sequences and series. You got to know the algebra around powers and roots and fractions, okay? So if you're not confident with that, you're going to struggle, okay? So square root is a power 1/2, and so therefore, is this convergent or divergent? We said that as long as r is greater than 0, so this is convergent to 0. Because r is greater than 0, 1 over n to the r is convergent to 0. Next one. Does not approach any particular value. Divergent. So a convergent sequence means that the terms get as close as you want to a particular value. They hone in or they approach a particular value. Divergent is anything else. Divergent is anything else. It's something like this, where it just keeps jumping and not approaching a value, or get infinitely large, like just keep increasing without bound, or increase without bound negative. Those are all divergent cases. So convergent means there's some real number that the terms get indistinguishable from. So close, you can pick any amount of tolerance. As long as you go out far enough with n, you'll get within that tolerance and never leave it. And then you can pick a smaller tolerance, and you'll get within that. That's what convergent means. Okay, what about this next one? So we can look at that interior argument as a rational function. What does that function do as x grows infinitely or very big? Here we have x to the 4th is our leading term over 6x cubed is our leading term. So that will do what as x increases without bound? That will get also increase without bound, right? X to the 4th. So this will essentially be x to the 4th over 6x cubed for large x, which will get really, really big. Because it's x to the 4th, there's one more x on the top. This is basically x over 6. And x over 6 just gets really big as x gets really big.
So it doesn't matter as another
No, when x gets really, really big, x cubed just wipes out x, right? It's way bigger than x. As x gets really, really big, x plus 2 just disappears, and the minus 5 disappears. You only consider the leading term for large x. So that ratio under the square root just gets really, really big. But we're taking the square root of it. Does that save it from getting really, really big? Taking the square root of it? No, that'll get really, really big, just slower. It'll get large slower. Divergent. Okay, ask me if I lost you. Okay, ask me if I lost you. Okay, so you should recognize that n to the minus 4 is just 1 over n to the what? 4. Here's one of those rules of exponents that you have to be confident about. This is 1 over n to the 4th. And so 4 is greater than 0 because 1 over n to the positive 4, therefore convergent to 0. Okay, why is this next one p to the n? Pi to the n over 3 to the n. So what is p in this case? You could rewrite this as pi over 3 to the n. Convergent or divergent?
Divergent.
Because?
Pi is greater than 3.
Yeah, pi over 3 is greater than 1. It's not between -1 and 1. It's greater than 1, therefore divergent, because we're not within the range -1 to 1. How about the last one? How can I write this as p to the n? Here's a technique we're going to see. We're going to be using a lot. We need to relate this to something to the n. So certainly, the pi is fine. So if we want it to the n, we can do pi over 3 to the n, but that's not equal to what we started with. What does 3 to the n plus 1 mean versus 3 to the n? It means multiply by 3 one more time, right? One more time. So how do I need to change this to make it equal? So exponents, the number of times you multiply that number together. So this is 3 multiplied together n times. But what do I have? Here I have 3 multiplied together n plus 1 times. So there's one more 3 multiplied in the product. So I just need to have one more 3 multiplied in the product. So do you see that those are equal? 3 to the n plus 1 is the same as 3 times 3 to the n. Because it's just one more 3 than 3 to the n. Divergent or convergent? Okay, that should be easy. Convergent, because we're dividing by 3. Convergent, right? Blank stares. Lots of blank stares. Is this convergent or divergent? All I heard was vergent. Con or divergent? Divergent. It's still the same one. It's still the same sequence, just every term is multiplied by 1/3. Again, it's going to get really, really large, just a little bit slower than the previous one. Divergent. Because it's still, p is greater than 1 still. The 1/3 doesn't change, doesn't make numbers getting really, really large stop from getting really, really large. It just slows them down. Just slows them down. 1/3 the rate, okay? Questions on any of these? Hopefully that helped. But there's an aspect to this that you can't do every type of example. You're going to come to ones that are a little bit different, and you have to use the tools that you have. And again, know your algebra. You got to know your laws of exponents. Last chance. Questions? Okay, factorials. So you may have seen this in the past. This is factorial. It doesn't mean 4. 4. It means you start from the number and you multiply it down. You always go to 1. You always multiply down by whole numbers all the way to 1. So the 4 factorial is 4 times 3 times 2 times 1, and that's the number 24. Okay, by definition, so we don't want to get into this discussion, but if you ever have 0 factorial, that's defined as 1. 0 factorial is defined as 1, not 0. That's another discussion for another time. Just remember that. 0 factorial and 1 factorial are both equal to 1. All right, so write out and find 6 factorial. Go. Write out and find what 6 factorial is. Okay, that should be easy. You're going to start at 6. You're going to multiply down by whole values until you get to 1. And you should get 720. 6 times 5 times 4 times 3 times 2 times 1. Okay, what about 28 factorial divided by 25 factorial? Now, when you represent 28 factorial, you don't want to write all 28 values. So you can use, just get it started, and you can then write dot, 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 and then how will it end? So with a 28 times 27 times 26, etc., dot, 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 and then how will it end? What are the last 3 values we'll multiply? 3 times 2 times 1. It always goes down to 1. Always multiplies from the starting value. Always multiplies down to 1. So see what happens when you, so express both 28 and 25 factorial. Don't write out 28 values. Don't write out 25. You can represent and so on with dot, dot, dot. And then see what happens. So when you don't do the math, the common mistake would be to say, oh, it's 3 factorial. It's not 3 factorial, right? It's not 3 factorial. So what happens, what you see is that within 28 factorial, what do you have? But inside 28 factorial, the tail of it to the right, starting at 25, is what? 25 factorial. See that? So what I've put in brackets in blue is 25 factorial. So every factorial includes every factorial of the values lower than that one, right? So 28 factorial has, as a left kind of, as a right tail, has 25 factorial in it. It also has 20 factorial in it. It also has 7 factorial. That's part of it, okay? And so that means that this all goes away, right? So 25 factorial is part of the numerator, and it's the whole denominator. So you just get 1 for that part of it, and what's left? 28, 27, and 26, whatever that product is. So that's, what is it?
19,656.
So that's what 28 factorial over 25 factorial is. So these factorial, this shows up in sequences and series, so let's do a sequence. Questions on the basics of factorial. Does it make sense? So what about this? Here's a sequence. So what I want you to do is write out the first 3 terms of this sequence. So what are the first three terms of the sequence? What would they be? And then we'll do the rest together. So just do this first line. Just write out the first three terms of the sequence. What would the first three terms of this sequence be? When you do that. So when n equals 1, you should get 1/6. 1/6 because you get 1 factorial over 3 factorial. When n equals 2, you get 3 factorial over 5 factorial, which is 1 over 5 times 4. Same thing happens as above, but it's just the larger factorials in the denominator now. So you get 1 over 5 times 4, and then for this one, you get 1 over 7 times 6. The 7 factorial has 5 factorial in it, and those go away. So here's the first three terms of that sequence. 1/6, 1/20th, 1/42nd. So if you were to just conjecture, looking at the first three terms, would you guess that this is convergent or divergent? Convergent to? Yeah, it looks like, this is not any proof, we're going to prove it in a second, but our conjecture would be these fractions are getting small fast, right? They're getting really small fast. And so we would think that this is going to approach 0, be convergent to 0. So let's prove that. So we prove that by, we're going to rewrite the sequence algebraically. We're going to rework this initial expression. So what is 2n minus 1 factorial? What's the first value? 2n minus 1. Just, it's the same thing we did before. You start with the first value. And then what? You go down, you keep multiplying by 1 less than the previous factor. So what's the next factor? 2n minus 2. When does it end? So where does it end? Where do all factorials end? 1. So they all go down to 1, so we can finish by saying 3 times 2 times 1. So that's what the numerator is. Start with the value that you're taking the factorial of, and then keep each factor is 1 less than the previous, all the way down to 1. That's what factorial means. So what would the denominator be? You write out the denominator? So what do you notice about the denominator? Do you see what does the denominator include? 2n plus 1 factorial includes 2n minus 1 factorial as a factor of it. Do you see it? Does it make sense? So once you get to 2n minus 1, now you're talking about 2n minus 1 factorial, which is the whole numerator. So what does this simplify to? One over 4n squared plus 2n. So that initial sequence is the same as the sequence 1 over 4n squared plus 2n. Convergent or divergent? Convergent to 0, right? Super easy, right? Super easy. That numerator is just going to get really big, and the whole fraction will approach 0. That's what we thought, right? That's what we thought when we saw those first three terms. We conjectured it's going to converge to 0. So this is proof of that. Is that a question? Yeah. What does 2n plus 1 factorial mean? It means start at 2n plus 1 and then do what? Multiply by the number that's... Start with the number 4 and you multiply by what? 1 less than 4. And then 1 less than that. And then 1 less than that. That's what factorial means. It means march down by whole numbers and multiply those all out. So what's 1 less than 2n plus 1? You see? 2n is 1 less than 2n plus 1. And then 1 less than 2n is 2n minus 1. And that starts the 2n minus 1 factorial. So those go away. Other questions? Okay. So now we're ready to talk about series. Okay, so that's our overview of sequences. And so let's review again. What's the difference between a sequence and a series? This whole conversation of this whole chapter means nothing if you don't know this. A sequence is what? List. It's a list. It's an ordered list. And the series is what? You take that list and you're going to add up all the terms in the list. So that's the baseline knowledge here. So working on any of these problems means nothing if you don't have this, okay? It's the baseline knowledge. So, given a sequence, A sub n, A1, A2, A3, A4, what's the associated series? Add them up. Add them up. So given a sequence, like the ones we've been looking at, if you now take those terms of the sequence and add them together, all of them, that's what we call the series. You remember from earlier in the beginning of the semester, we had a compact way or an abbreviation for sum, and that was the sigma notation. So that's what we're going to use to represent these summing up of the terms of a sequence. We use the summation notation. So this is what we say. So it's the sum of A sub n, the sequence, n starting at 1, and just going on and on and on, getting large without bound. So, starting value of n, this represents that n will never stop. It'll just keep getting large. And that whole expression then represents n equals 1, then n equals 2, then n equals 3, and then you're summing them up. That's what it's Greek sigma for sum. So we're going to see a lot of these in the next couple weeks. A lot of these. But you have to have the right mindset. When you see that, you always think this. Whenever you see that, you think this. That's what it means. This is another base. So for series, here's the baseline knowledge for series. Doesn't make sense to analyze all these sums, these series, if you don't have this mindset about them. Okay, that's the intro. Any questions on that? Okay, so here's an example. 2n minus 1 is the sequence. So I want you to rewrite this in summation. If we rewrote this in summation notation, it would be the sum of 2n minus 1. And so I want you to write out what that means. Go, write out what I just put up there, write it out explicitly. What does it mean? Okay, you should have gotten this. That's what that means. First term of the sequence is 1. Second term of the sequence is 3. Then 5. So this is basically the odd numbers. The sequence is the sequence of odd numbers. Series means add them up. And what's going to happen when we add up all the odd numbers and never end? What are we going to get? Yeah, it's certainly going to just increase without bounds, right? Increase without bounds. So that's the idea of a divergent series. This is a divergent series, since that sum just gets large without bound. It gets large without bound. Okay, so I want you to do the same for this one. Write out using summation notation, and then write out what it means. Write out the summation notation for the series for the sequence, and then write out what it means. So hopefully that's the easy part. We're going to sum up 1 over 2 to the n as n starts at 1 and just marches up. We're going to talk about that. Okay, so you should have had this. This is what it means. 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, etc. Okay, what about this? So what's your reaction to this? Okay, convergent to 0. What do we think? Agree with that? Yeah, so you're starting at 1/2 and you're adding values to that. So the sequence converges to 0, yes. But now we're adding them up. So the series, what do all the values add up to? So it's kind of like the turtle crossing across your backyard. And that's what you were thinking, wasn't it? All right, so it's like you got this turtle, okay? And it starts on one end of the backyard. And the first day, it goes halfway across. Day 1, it makes it halfway across. That's 1/2 of the way. And then on day 2, it goes 1/4 of the way across. Now, how far has it made in total? 3/4, right? So now 1/2 plus 1/4, the turtle has made it 3/4 of the way across the yard. The next day, it goes half as far. What's its total distance now? Now it's made it 7/8 of the way across the backyard. Next day it goes half as far as it went the previous day. It's always going half as far or going half the distance to the other side of the backyard. So every day it goes halfway to the fence. So if it were to go for an infinite number of days, how far would it make it across? It would make it, right? So if the days just went on and on and on and on forever, and we can imagine that, then it would make it to the other side because it keeps going half the distance it went before. Therefore, this sum equals it equals 1. You say, but you never really get 1. Well, you do if you can add all the terms together. And what's all the terms? An infinite number of terms, okay? So if you ever stop adding, correct, you did not make it to 1, or the turtle did not make it to the other side of the backyard. But if you have all the terms, meaning you never stop adding terms, that sum is essentially 1. It's so close to 1, it's indistinguishable from 1. Okay? Okay. So this is a convergent series. Why? Because that sum equals a real value. If you were able to add all the terms together, you'd get a real value. So this is convergent. And if it's convergent, that means that sum equals a real value. In this case, 1.